What if, on a distant icy moon, life has managed to thrive? Today, we delve into groundbreaking NASA experiments that suggest Europa and Enceladus may not only conceal vast oceans beneath their frozen exteriors but could also preserve complex organic molecules, such as amino acids, just beneath their icy surfaces. This video explores the intricate science behind these findings and why they could be a turning point in our quest to discover life beyond Earth. So, without further ado, let's begin. NASA's latest experiments have taken a major step forward in astrobiology. Scientists have recreated the extreme conditions found on Europa and Enceladus, focusing specifically on radiolysis, the breakdown of molecules under radiation. In a simulation chamber chilled to a frigid -321 degrees Fahrenheit, researchers exposed amino acids to gamma rays, a form of radiation common in the outer solar system. This experiment closely replicated the radiation-rich, ice-covered environments of these moons. The results were astonishing. Amino acids not only survived but did so at surprisingly shallow depths. On Europa, they remained intact up to 20 centimeters below the icy surface, particularly in areas shielded from frequent meteor impacts. Enceladus provided even more promising results, with crucial molecules enduring just a few millimeters beneath the surface. These findings represent a major shift in our approach to space exploration, suggesting that missions to these moons could be less complex and invasive while still yielding valuable discoveries. Moreover, understanding how these organic molecules persist in such harsh conditions helps scientists predict potential biosignatures of life. Amino acids, the essential building blocks of life, play a crucial role in protein formation and biological functions. Their presence near the surface makes exploration missions more feasible and minimizes the risk of contaminating these celestial bodies, aligning with planetary protection protocols. If life's fundamental components can survive on these moons, it raises an even bigger question. What other secrets lie beneath their icy surfaces? Should we discover life on Europa or Enceladus, what forms might it take? The conditions on these moons are drastically different from Earth's: dark, frigid, and under immense pressure. Any hypothetical life would need to be extraordinarily resilient, possibly evolving in ways unseen on Earth. Such organisms might rely on chemosynthesis, deriving energy from chemicals rather than sunlight, and could have developed unique metabolic pathways to endure their extreme environments. Theoretical models suggest that life in these subsurface oceans might be vastly different from anything found on Earth. In complete darkness, organisms may lack eyes or have evolved specialized sensory organs to navigate and find food. Their biochemistry could be adapted to process the saline, mineral-rich waters, turning what would be toxic to most Earth life into a vital energy source. Recent experiments have provided crucial data to better understand how amino acids survive in extreme conditions. Scientists discovered that bacterial cellular material might protect amino acids from reactive compounds formed by ionizing radiation, which can break chemical bonds or create destructive molecules nearby. This suggests that microbial life on these moons could shield crucial organic molecules, enhancing their survival chances. Additionally, researchers have established radiolysis constants, rates at which amino acids break down under radiation. Using these measurements, they have identified optimal drilling depths and locations where these molecules are most likely to endure radiation-driven destruction. This marks a significant advancement in astrobiology, as it is the first time experiments have applied lower radiation doses that do not completely degrade amino acids, preserving them for scientific analysis. It is also the first study to assess their survival in simulated moon-like conditions, including their interaction with dust, which could complicate detection and analysis. As astronomers plan upcoming missions to Europa and Enceladus, how will they explore these moons? Will they simply capture images, or will they collect physical samples? The answer is both. Future missions will be equipped with cutting-edge technology to conduct extensive orbital observations and land-based explorations. The Europa Clipper mission, set for the early to mid-2020s, will perform detailed orbital studies, capturing high-resolution images, mapping surface features, and analyzing Europa's icy exterior. Meanwhile, robotic landers will be designed to endure the Moon's extreme conditions, directly analyzing ice and subsurface materials for signs of life, such as amino acids. These landers must be engineered to withstand intense radiation while operating at depths where biological signatures are most likely to be found. Additionally, missions like the Enceladus Orbolander concept from Johns Hopkins University will combine orbiter and lander functions. This innovative design would allow direct sampling from Enceladus's towering plumes and potential hydrothermal vents, areas rich in warmth, nutrients, and energy that could sustain life. Past missions such as Voyager 1 and 2, along with the Galileo spacecraft, have provided invaluable data on these moons' magnetic fields, surface compositions, and subsurface oceans. Their discoveries have greatly influenced the design of new spacecraft capable of surviving and operating in the extreme environments of Jupiter's and Saturn's moons. Voyager 1 and 2 expanded upon earlier Pioneer missions, delivering detailed images and data on gas giants and their moons. Voyager 2, in particular, is known for its flybys of Jupiter, Saturn, Uranus, and Neptune, offering unprecedented glimpses of their moons, including Enceladus's icy geysers. Galileo, specifically tasked with studying Jupiter and its moons, orbited the gas giant for years, providing critical insights into Europa's subsurface ocean and potential water plumes. Its findings have played a pivotal role in shaping the scientific approach to exploring these icy worlds. The knowledge gained from these missions is vital in designing future spacecraft that can endure extreme radiation, vacuum conditions, and frigid temperatures. Thank you for joining me on this journey through one of the most exciting frontiers in science. As we continue to push the boundaries of exploration, let us move forward with curiosity and a commitment to responsible discovery. Keep watching, keep wondering, and most importantly, keep exploring.